Hello, everyone, and welcome to this short but powerful lesson on gradient descent. That is one of the key ideas behind how machines learn. We will break everything down step by step using simple language, real intuition, and fun examples so the concept sticks with you. Why do we need gradient descent? Well, when we train a machine learning model, we're basically trying to answer only one question. What settings for my model make its predictions as accurate as possible? To measure how good our model is, we use a number called a cost. A high cost means poor predictions, a low cost means good predictions. But here is the challenge. We can't test every possible value of the model's parameters. There are simply too many possibilities, especially in big models. So we need a smart way to search for the best values. That smart method is called gradient descent. Let's create a fun mental picture of gradient descent by using a landscape analogy. Imagine the cost function as a giant outdoor landscape. High areas are hills, which give us bad predictions with large costs, and low areas are valleys, which give us good predictions with small costs. You start somewhere on this landscape with random parameter values, and your mission is basically to find your way to the lowest valley, or what we call the local minimum. But you don't have a map. You can only look around your feet and see which direction slopes downward the most. This is exactly what gradient descent tells you to do. Look around, find the steepest downhill direction, take a small step, and repeat. If we keep doing that step after step, we naturally end up at the lowest point, or the local minimum. Gradient descent works by following a simple rule. At every point, move in the direction that reduces the cost the fastest. That's it. That's the rule. Each step slightly adjusts your model parameters, like W, B, or hundreds of others in larger models. Every step also makes the model a little better, reduces the cost, and moves you closer to the best possible parameters for reaching the local minimum. We always need a starting point, so let's start the journey by choosing initial values for our parameters. A very common choice is to simply start with W equals 0 and B equals 0. It's not magical, it's just simple. From there, gradient descent begins improving the values step by step. In larger models, you might start with small random values instead, but the idea remains the same. Now let's see how the algorithm moves. Here is what happens during every update. First, looking around. The algorithm checks the cost changes if you nudge the parameters in different directions. Second, it finds the steepest downhill direction. This direction guarantees the quickest drop in cost. And third, it takes a small step, not too big because it might overshoot, not too tiny and small because it will move simply too slowly, and we don't want that. And the last step, or the fourth step, is that it repeats. This continues until the steps barely change the cost anymore. When the cost stops dropping noticeably, you have likely landed at a minimum. This point is called the local minimum. Sometimes the landscape has multiple valleys. One valley might be very deep, which is a great solution. Another valley might be shallow, which is not ideal, but still a minimum. Where you start determines which valley you end up in. This is why different initial values sometimes lead to different solutions, especially in deep learning. For simpler linear regression, the landscape is smooth and shaped like a nice bowl. There's only one lowest point, so no matter where you start, you end up in the same place, always. Let us explore why gradient descent matters so much. Gradient descent is not just a tool for simple regression. It is everywhere. It is used in linear regression, logistic regression, neural networks, deep learning in LLMs or large language models, image recognition models, and recommender systems, and all sorts of models. Whenever a machine needs to improve itself by minimizing a cost, gradient descent is usually doing the job behind the scenes. Learning this algorithm gives you one of the essential building blocks for understanding modern AI. In the next lesson, we will translate this intuition into the simple math that powers the algorithm. You will see exactly how each step is computed and how we apply this in code. Let's continue building your machine learning foundation. See you in the next lesson.